Hello everyone, this is Qian, and today I'm going to talk about one of my recent work on the approximate MDL theory, and in this work, we try to answer whether imperfect combination also implies good prediction. And this talk is based on a joint work with Xinyu Mao, Shanghua Teng, and Guangxu Yang. Let me first recall the notion of induction and universal induction. Induction basically means to predict the future based on the past. And here we can model it simply as a sequence prediction problem. Specifically, at each round t, we can see the past data x1 to xt, and the goal here is to try to predict the next data x t plus 1. Actually, a sequence prediction problem is quite expressive. It can describe almost all prediction problems, such as the weather prediction, the stomach prediction, and in particularly, it can also describe supervised learning. So to see why, we can imagine that the machine learning problem can be viewed as predicting the label of the test data given the past training data. And in this work, we are particularly interested in universal induction. And in this context, we make no assumptions on such as ID on the sequence on the data, except the only a assumption that the infinite sequence is computable, meaning that this infinite sequence x1, x2 to x infinite can be generated by an unknown deterministic or randomized algorithm. And you may wonder whether we can have such an amazing, such an universal predictor. Actually, there are two well-known universal predictors, namely Solomonoff induction and the MDL method. And today, I will focus on the MDL method. The basic idea of MDL is simple. The basic idea is that at each round, we simply choose the program that best compresses the past data, and then use it to predict the next data. And here, to describe the data, we use a two-part code. And the first part is the length of the program, and the second part is the arithmetic code length of the data given that program. So formally, at each round t, the MDL method select a program that minimizes such an score, and then use such a program to predict the next data. Poland and Hart prove that such a simple MDL method is already a universal predictor, meaning that the total prediction error across all of the infinite number of rounds is finite. So we can conclude that the MDL method can eventually learn the true mechanism. MDL has formalized the idea that compression is prediction. However, the classical MDL theory requires exact optimal compression. But we know that in practice, compression, which typically corresponding to training, is really exact optimal, and typically the training is only approximately optimal. So natural question here is to ask whether approximate compression also leads to a good prediction. Actually, another motivation to study this question is that potentially approximate compression can be more efficient in computation in principle. And in this talk and in this work, we provide almost a complete characterization of this question. And here is our answer. And our answer is that at each round t, we allow the MDL method to choose a program whose score is at most say above the optimal. And then we can prove that it still implies reliable prediction, meaning that the total error is still finite. Furthermore, we also studied the MDL score with a general regularization weight, lambda, and we can prove that lambda equals 1 is really threshold. Specifically, when lambda is less than 1, then the MDL method can overfit, meaning that the total error across the infinite numbers go to infinite. But in contrast, if lambda is at least 1, then the MDL method is guaranteed to be reliable, meaning that the total error across all the infinite round of across the infinite number of rounds is still finite. So basically, our result has two main messages here. And the first message is that we prove that approximate compression also implies reliable prediction, but it requires strong regularization weight. Specifically, it requires lambda is at least 1. And second, we can see that here smaller approximators like C gives a smaller error bound. So in this sense, our results also implies that better conversion gives better prediction. Before moving on, I have a remark here. Actually, there are already several papers making the claim that better conversion gives better prediction. However, as far as I know, these papers use a different meaning of compression. Specifically, they are talking about in-context compression, whereas the model parameters are fixed. And then the compression method uses the model to compress the data in the context. So in the meaning, the claim that better compression is better prediction is true, but by definition, because better compression is defined as smaller prediction log loss. In contrast, in this work, we use another meaning where we compress training data directly into the model parameters. Actually, one motivation of this work is to try to understand why transformer is better at prediction than other architectures. We know that empirically transformer is better at compressing human knowledge, like Wikipedia, but why it implies the transformer predict well is still unclear. And actually, this paper can be viewed as a initial step towards explaining this practical success. Now I want to talk about the future direction. Here, my big goal is to build a practical universal predictor. Here, I suggest that we can only focus our attention on bounded computable environment rather than all computable environments. Here, bounded computable means that the underlying program is constrained by its time capacity and space capacity. Here, I claim that this restriction does not lose university because we know that real-world environments are implemented by finite physical systems, and so its computational resources must also be bounded. For example, based on very basic physical laws, such as information cannot travel faster than light, Celluloid proves that any physical systems with mass at most 1 kilometers and volume at most 1 liter can perform at most about 2.4 times 10 to 15 operations per second, and it can store at most 10 to 31 bits in its memory. So if we only consider bounded computable environments, then Solomonoff and MDL are computable. So the central question here becomes how low the computational capacity can go. How much memory and time do we need? Actually, we care about this question because it has also implications on AI safety. For example, suppose that an adversary builds an AI agent, and we know nothing about its structure, its design, except that we know that this AI agent is implemented on S-bit memory. And then the question is to ask how much memory does a defensive agent do we need to predict the adversary AI agent and then counter it. Is it poly S base enough, or we require at least exponential of S number of base? And actually, this work can be viewed as the initial step towards this question, because potentially approximate MDL theory has lower computational capacity. Here, let me share one partial result from our ongoing project. And here we can prove that randomized environments are much harder to predict than deterministic environments. Specifically, for a deterministic environment, the predictor that uses can use only S plus K memory. But for randomized environment, no fixed memory bound is enough, and the needed space goes to infinite as the round n goes to infinite. Now let me conclude this talk. This talk we propose another universal induction method called it approximate MDL, and this kind of universal predictor may be weaker in its prediction performance, but the benefit of this kind of method is that it requires less computational power. Here, for future directions, the big goal here is still to design or to build a practical universal predictor. And here, I think a computational capacity theory should and would play an essential role here, because the barrier to build such an universal predictor is that the existing method, such as Solomonoff and MDL, has too high computational capacity. Okay, and finally, let me make a quote from Minsky, and he says that the AIT-based method would make better predictions than anything we have today, and everyone should learn all about it and spend the rest of their lives working on it. Yeah, that's all. Thank you.